Hello, everyone, and welcome for tuning in. I'm really sorry that I can't be in Japan in person, but let's hope that maybe by next year everything is back to normal and we are all being in the same room and having fun together. I'm really missing that. I'm not a big fan of webinars, but hey, it is what it is, right? So today we're going to talk about systems that meet users' expectations. Users today have a very specific expectation, and we're looking into that in a couple of seconds. But what they basically expect is a system to be online. And how to do that means we need to be resilient, we need to be fault tolerant, we need to be high available, we need to be scalable. We need to be able to satisfy the demand, basically. So imagine you're being the user and you want to do something. You want to transfer money. You want to online shop. You want to do just something, right? So you go into your computer, you hack in the URL, you open up the program, and the only thing that's going to happen is you're being dissatisfied. Why? Because it's not working. The site is not available. The program can't log in. You stand around, you sit around, and you're being, you know this feeling, right? Something is not working. And it's okay if it's just a couple of minutes, but if you really need to do something urgent and the system is not available for hours, that is really a pain. So who am I? I'm Chris. Some of you may know me from the couple of years before, when I was still at Hazelcast or at Instana. Today I'm here as co-founder and the chief software magician, which is our term for CTO, from Cleverbit. And from my own personal background, anything related to performance, anything related to performance engineering, developer relations, fairy tales is just mine. With fairy tales, I mean any kind of performance comparison, right? Is AMD faster than Intel? Is Intel faster than AMD? Is AMD faster than NVIDIA? Is NVIDIA faster than AMD? Is anyone faster than the other? And why I'm saying that, I think there is a very important fact about all kinds of benchmarks. Benchmarks are just as good as the person running them. There is a couple of folks that are really into benchmarks, and they try to be as honest as possible. We tried that at Hazelcast. We always tried that at Instana. I know the folks over at TimescaleDB really try to be honest. Like, hey, there is use cases where timescale is better than the rest, but there's also use cases where it is not. And the most important factor for me in terms of benchmarks, and that is important for scalable systems as well, is run your own benchmarks. Make sure that the benchmark, the data set you're using to run the benchmark, is as close as possible to what it is in production. Otherwise, you're going to have a problem. All right, a couple of words to Cleverbit. We are a cloud platform for animal husbandry. That means anything from animal fattening to the slaughterhouses to anything like that. Why would we do that? We want to increase animal welfare. I know that in Japan, animals are really something different, and you guys are a big fan of making sure that animals are healthy and they feel good, and because the quality gets much better, the meat quality. But for the rest of the world, unfortunately, a lot of countries, including Germany, are not as, well, simple on that. So for us, it's important to understand what factors influence animal welfare, what factors influence animal healthiness, what kind of medications are given to the animals, and that we can present all those information in the end to the consumer in the supermarket, so he or she can do an educated decision on which meat to buy and which not. Right, so that's just what Cleverbit does. If you're interested, I'm happy to talk more about that in a one-on-one. So from a user perspective, you remember I said people and that includes me and probably you as well, don't like system outages. And they go rampage about that. So just the other month, somewhere early October 4th, Facebook had a couple of hour outages. And it says 7 hours. And 7 hours of an outage on Facebook brings it a Wikipedia page. So there is a specific Wikipedia page on the English Wikipedia about the Facebook outage in 2021. And that is insane. Can you imagine we would create Wikipedia pages for every single outage that we have? But that is not the only thing, right? Facebook is just like the massive example, but there's more. In April, I think, April 2021, there was a bigger outage with one of the biggest CDN networks, content delivery networks, called Fastlane. And Fastlane, it just doesn't have a single customer, but they have a lot of customers. And just like the outage a couple of years ago, where one of the DNS providers were under a heavy DDoS attack, and basically half of the internet was gone, kind of the same thing happened with Fastlane. It was not like half of the internet, it was, well, maybe a quarter, but it was a big chunk. And that are the news of today, right? There is a service that can bring down a quarter or a half or maybe even more of the internet. And that is what all the newspapers, all the news outlets are actually talking about, because it is unexpected these days. Imagine you want to look up a phone number and the online service is not available. You cannot do that. You have no idea how to look up the number otherwise. In Germany in the past, we had paper books where all the names and all the numbers were listed per city. So you had the one of your own city, but the second you wanted to call somebody in another city over, that was it, right? You were basically forced to call the number to ask for, hey, I'm looking for that specific person in that city, and they gave you the number or just connected you through. So what all that means is people expect services to be available and to work. That is what it is, right? The problem is software fails, and software and hardware also, so hardware also does, right? We all know that systems fail, software has bugs, hardware has a malfunction, and the service becomes unavailable. So what should we do? We need to, doesn't that prevent us from actually building systems that are meeting users' expectations? And not specifically. There's a couple of really important factors that you can introduce into your architecture that you need to think upfront to understand, okay, that can happen, that may happen, and that is how I mitigate it. One important thing upfront, and it will be repeated over and over the whole presentation. There's one important factor. You have embraced the fact that there will be failures. In software, in hardware, in networking, in wherever. The second you understand there will be failures and I cannot do anything to mitigate that, the second you are one step further than the rest of the industry. So the first thing is resiliency or resilient systems. And I really, really like the fact how Google tries to explain resiliency when you Google for it. It says it is the capacity to recover quickly from difficulties. They also add toughness afterwards, but we're gonna ignore that. It is a tough option to do that. But the important thing is when something goes wrong, you remember, embrace the failure, something will go wrong. If something goes wrong, we need the option. However we do that, to quickly recover from that failure and make sure that the system stays available. The other thing is high availability. And high availability means it is the characteristic of a system which aims to ensure that an agreed level of operational performance, which most of the time is uptime, can be satisfied, right? So high availability often comes along with having multiple instances of the application with a load balancer in front of it. And when clients or users connect to your system, you reroute them to one of your instances to make sure that you can have, well, maybe not exactly 4 times, depending on how linearly scalable your system is, but to have a higher degree of users being satisfied by your system, which still looks like one component, but in reality is not. And there is one very important factor between high availability and the next thing, which is fault tolerance. So high availability just means we want to satisfy a specific performance expectation, whereas fault tolerance means we want to be able to still satisfy, well, maybe not all of it, but maybe 90% of this expectation, even if components fail, right? So that means if we have like the 4 different systems that all share have the same services deployed, when one of those components fail, we still want to be able to at least satisfy a certain amount and to make sure that users may get a little bit lower response times or slower response times, but the system in itself still behaves. It still answers your question. And if it doesn't, it should not just throw some weird error. It should actually try to tell the user, hey, there is a mistake in the system. We're working on that. We figured out there is a problem. We're monitoring the systems. We are already working on that, and we're going to fix it for you. So the difference between high availability and fault tolerance, and unfortunately, oftentimes I see people don't really distinct between those two things. High availability means we want to make sure that we satisfy performance expectations. Fault tolerance means we want to make sure that we can go on, or we are still available when something in the system goes wrong. And that all plays it back into resiliency, because if a component fails, we need to make sure that we can restart it or whatever to get back into the system flow where it is supposed to be. And the last thing is scalability. And that kind of plays into this high availability system again, right? So scalability means we want to be able to grow with our user expectation, with the amount of work that is increasing over time. So we need to be able to scale our system, which means we most probably want to add additional instances of our components to the system to keep up with the increase of load. So I already said it a couple of times that there is basically one specific feature that goes hand in hand with all of those things, and that is multiple instances. Multiple instances, from my perspective, is the biggest factor to make sure that a system is resilient, that it is fault tolerant, that it is high available, and that it is scalable. Well, for scalable, it's a basic requirement. So, but there's 2 different ways of doing that. There is like a typical cluster, real cluster solution. So that means most of the time, data is partitioned throughout all those different instances, and they may have some secondary replica just to make sure that if a component fails, that the replica can take over. And in the best case, it's a streaming replica, so it's only like a couple of milli to nanoseconds behind the actual primary, so it doesn't really matter, right? You remember fault tolerance? So just having one of those is not specifically fault tolerant. There's the second option where you actually have backup data from another node on a different one. So for example, the first node could also have the backup from the third one, and the second one from the fourth one, and so on. But the more common system that I see these days is that you actually have a secondary replica behind it. So every node has one streaming replica that can take over in case of a failure of the primary. The other alternative is a full replication setup. And that is something, for example, that Postgres does. So in Postgres, you have a primary. The primary takes in all the write operations and makes sure that all your ACID compliant transactions are actually what you expect them to be, right? So you want to see that my write operation goes through and you know that it just works. But then they keep secondary replicas or secondary mirrors that replicate the original primary system bit by bit, basically, and make sure that if one of the primaries goes down, well, who cares, right? We have a streaming replica, so we can just fail over to the other system. And there's two really interesting factors about these two different ways of replication. So for the first one, because the data is partitioned, if you have a really read-heavy operation, which is extremely parallelizable, because it actually just asks for specific data on partitions, it doesn't have to do any kind of aggregation or other operation. The cluster with the partition data is much better because you can spread out the operation. Everyone is working on its own data, and you get the intermediate results back, and you just merge them together, and you're done. For the replication setup, when you have this system is much better when you have a heavy read use case, but the reads normally do like aggregations, sorts, any kind of those kind of things, because then it is better. You can still spread it out, right? As long as you don't need to do any write operation, you can go with a secondary replica and say, hey, I spread out my reads, whereas all the writes are still going to the primary. So there is different use cases for different scenarios. And for replication, you often also have the chance to say, hey, I want to have synchronous replication, or I want to have asynchronous replication. Asynchronous replication obviously gives you faster write operations, but your secondaries may not be perfectly in sync. For synchronous replication, the actual transaction is only finished when the secondaries tell the primary, yes, we are done. We applied this transaction as well, and now do the two-phase commit operation to the final commit. The other thing which is really important, and that is part of a little bit older diagram, but that is part of the system that we build, is a microservice-based system. Microservices give you the option. Well, they are not the silver bullet, right? Don't get me wrong. Microservices are not the silver bullet that other people want to tell you they are. They bring in a whole different set of issues that we kind of want to keep aside today. Just to mention a few. Remember, microservices need to communicate, so you have a lot more network interactions in between. You need to schedule them, you need to execute them. Kafka is a great solution, don't get me wrong. We also use Kafka, we love it. But in general, microservices just give you a whole bunch of different issues. They solve the old ones, they give you different ones. Anyway, so microservices are great because you have the option to say, hey, I can focus on a specific problem. And from my perspective, the bigger benefit of running microservice setups is I can scale those components, those parts of the system independently. Not every component in the system has the same requirements for scalability, right? Something that does a batch job overnight that nobody really depends on until the next morning doesn't need 20 instances. They don't help. It's a batch operation. They don't really help you being faster. However, on the other side, I have an online shop that does something on the invoicing or on going down to the payment processor like Stripe, and you actually lose money the second this system is not keeping up with the user's expectations, with the user response time. You're using real money, and that is where you need to scale, right? So microservices give you this amazing functionality, this amazing benefit that you can scale parts of a system to a higher degree than other systems. That obviously doesn't always work because some systems have dependency trees. Obviously, you have to scale the dependencies as well. But in the simpler, broader term, they give you an amazing functionality. And you see, we have quite a few services. And that is not all of them. I actually lost track of how many services we have these days. But we really split them down, not all the way that people sometimes say it should be just like one function or two functions. We decided that we either have like a functional component, like it is a protocol decoder that takes in some data and understands how to transform those data into our internal generic data protocol. Or on the other hand, it is something like one service does all the handling, all the CRUD operations, all the caching for farms, another one for barns, another one for customers. So we split them basically by some kind of a resource type system. And then we also split them by internal services only and external services, which do additional authentication and authorization flows. But microservices bring in, as I said, a couple of more issues. So now we have a lot of systems and we have a lot of public services, users logged into our system once. So how do we make sure that users stay logged in? How do we do stuff, right? And people normally tell you, if you want to have a fully scalable system, you have to go stateless. And don't get me wrong, I agree with that statement, but it didn't work for us. The second we wanted to do, first of all, what we did is we locked the user in. He got a JWT, so a JSON Web Token. And because we wanted to be completely stateless, we stuffed everything into this token, from permissions to user roles to available, accessible customers to, I don't know, what else, right? So the token just grew bigger and bigger. And we have a very detailed, fine granular permission system because on farms, you have a lot of different people and not everyone is able or should be able to do anything or everything. So our tokens just grew bigger and bigger up to the point where we said, okay, that doesn't seem to be a feasible way. It doesn't seem to be what we want. So what we set as our internal standard, we want to be as stateless as possible, which means we still use JWT tokens, but for the first step of authentication. So we have the JWT, we can test if the public key or if the signature is correct. And that already keeps away like most of the work from the system if the token is expired, if the token is not validly signed, stuff like that, right? So we want it to be as stateless as possible. Then we take the token and send it to our internal authentication service, which is heavily cached, which has multiple instances. And that one gives us back like, hey, these are the actual customers that this token can access. These are the roles the user has. Those are like the permissions with all of the ACLs applied. And that comes back and then, hey, cool. So in broader terms, that means if you really want to go stateless, you have independent counters, as in this example, right? So every service has its independent counter, which sounds like a great idea, but now how do you implement something like rate limiting? How do you know how many calls the user overall executed against your API. You can solve that when you have a load balancer in front of it that is sticky or a sticky session, but I'm not a big fan of that either, because late is at the point where you have to fail over to another instance, your counters still are broken. So what we do is we have shared counters, but we have specific services only doing that. And most of them keep the information in Hazelcast, for example. And you may figure out of the rest of the session that I'm a big fan of companies I work with. I really love their technology. They're normally pretty well selected by me, because otherwise I wouldn't join them. And Hazelcast and Instana, we will see Instana in a little bit, are definitely part of that. The next thing is an event-driven architecture. And if you remember this picture, every block is basically connected through message queues. Message queues for us means we have Kafka in place over and over and over again. For what reason? Because it gives you a great way of saying, hey, certain parts of the system need to be rebooted, but we don't want to lose data. But it doesn't matter if the data is processed like a couple of seconds later. So one side is keep pushing into Kafka. Well, actually for us, it's Azure Events Hub, but we take that aside. And on the other side, you restart the service, but the second you reconnect, you get all the data. The other really nice benefit is that you have replay at least for a certain amount of time. So if your system fails for some reason, you have to do some maintenance for an hour and a half or whatever, there's always the chance to replay certain operations or to replay the messages, which is great. Also, when you, for example, have to roll back to an earlier version of your database for whatever reason, you can just replay all the operations. For us, that means everything that comes down on the left side, everything that comes in through the ingress pipeline or data ingress adapters, that is our ingress pipeline, that itself has a Kafka message queue. And then when it goes further down, it hits a couple of more. From an operational point of view, it gives you a couple of more issues. And I have just one example here, which is our Webhook implementation. And you see there's at least 3 message queues, and I'm not even sure if that was the final state. That was I took this from an earlier version of our technical design document, but we have at least 3 message queues. We have the data ingress, then we write down to the database. We see if we have subscriptions to keep data or to push data onwards to our external partners, and if there's a subscription, we push it to the next message queue. We create the actual messages, we sign them, we publish them, which means we put them yet on another message queue, and that goes on and on. And if the publish or the actual webhook operation fails, we do not acknowledge that we handled this message, but we send it back and say, okay, fair enough. We need to retry that at a later point, and we're actually doing exponential backup, so we always keep a little bit longer until I think 12 hours later we throw away the message, something like that. But to keep all of that in check, and you see there's a lot of connections between different services, and that is just part of the system, right? But there's already a lot of connecting dots and connections between different services, which means there's a lot of dependencies. To keep all of that in check, you need a good tool for observability. And the further you go down the road of implementing microservices, implementing message queues, implementing those kinds of things, the more important it is that you really, really have the chance to keep an eye on your system. And keeping an eye on your system also not only means like, what are the dependencies between my systems? It also means like, okay, what is the scalability factor? Do I have what's the term? Do I have single point of failures? Do I have systems that slow down the rest of any or the rest of the system without actually having a failure, right? But it also means you need to quickly understand if there are failures in the system or not. And for example, with Instana, you have a couple of different ways. You can show yourself like, what is the dependency tree of my specific service? How is the infrastructure laid out? And you see in this example that shows all the hosts that we have, for example, at Cleverbit. And you see that there is like at least one service which has a little bit of an issue right now, this like red bar or red piece in the upper information. And to be honest, I just took it, and as I said, from my perspective, that is not a big deal. You will have failures. We just have to embrace this fact. So I just took this picture at a random point in time, and obviously something failed. Like there's at least one red piece all the time, or one red component all the time. It just matters how fast you can figure out what happened, how fast you can figure out how to mitigate this issue, and how fast you can go back to where you want to be and how to fix the issue. But that is just the infrastructure point of view, infrastructure also in terms of services and applications. But it also goes a little bit further down, right? You also now have a very distributed system, and you need to understand how those services work together. What is my response time? What part of the system corresponds to what response time, and how do they sum up? So basically, what do my users think about the system? How do they feel about the system? And then again, I'm a big fan of Instana. I love it. And we use it quite extensively. You see that there's a lot of different database calls to just respond to this one operation, which is in this case an analytical call to our backend. But we see that it has a couple of requests against the database to get like basic data. There is also a couple of cache operations, but they're so small that you can't really see them. And then it goes down to the internal service that does the actual select against our time series database to get all the information. While that kind of looks fairly simple, that is an API call, which is pretty much straightforward. It can get pretty extensive when you, for example, look at the operations from our data pipeline, ingress pipeline. So all the way on the left, we have the service that receives the actual message. We drop it onto the message queue. We have our center part, which does all the message decoding, all the possible data adjustment, additional calculations, whatever we have to do. And then we have the right part, which does alerting and writing down to the database and whatnot. And this is something that you can't really grasp anymore as a user who is not able to go down to that level. There is a complexity, and even or especially because of the message-driven architecture, event-driven architecture, there's a complexity that is hard to grasp. And Instana, I really love that. It gives you like two different views of the same trace, and it gives you the view by technology. And you see that there is different colors, and those different colors show you things like there's database calls, there's GDPR calls, there is caching call or services calls against caching services. There's different stuff, and the colors basically show you what type of technology it is. And then there is on the right side, there is the graphic by endpoint, and now the colorization shows you what service or how many different services you hit. So every single color basically shows you gives you one service. So that means in this picture, we have, to be honest, I don't know, 15, 20-ish services. So now try to imagine you have to figure out an issue somewhere in between, and you have no clue. The great thing about Instana, and I unfortunately forgot to include a picture, Instana shows you where exactly in your operation an error happened and gives you the option to trace back where the error came from or how it happened. But that is just Instana. At Cleverbit, we use more tools, and I don't want to say you cannot have enough tools, but you're getting pretty close. So we have at least 3 different tools to understand errors from our users or from the backend. We use Instana very extensively in the backend tracing, backend performance engineering, and trying to figure out how to optimize stuff, where slow operations are, where slow queries are, and stuff like that. We also use it to understand calls from our website and how those calls correlate to the actual backend operations. So you can see if you have like a web session and that one does like 20 operations against the backend, you can see all those operations, the specific backend calls or the specific backend operations for that call or for that session with the user's website requests and how all the load time was and all that. But for JavaScript errors, even though Instana can do it, we found Sentry to be a much broader and much better support for that. So Sentry captures all the errors for us, especially because we have web frontend and mobile frontend, and Sentry just captures both of it. For us, it is great. It captures a lot of the stack traces. It captures what happened before and what happened after. It captures the error message, and it just tries to give you as much information about those weird JavaScript errors as possible. And then we have Smart Look, and Smart Look is really specific. Smart Look takes basically a film or a recording of the user's session. So it captures the mobile application as part of screenshots. It captures the web browser as screenshots, so at least the part of the application, and shows you where the user clicked, what happened when he clicked. It disables or it removes all the text fields and drop-down fields and stuff from the pictures, so you can't really see anything like inputs or something. It just shows you the flow. And most of the time, that is really helpful when you have an error and you can't reproduce it, and you watch those recordings, and at some point you're like, oh, wow, so that is why it happened. That is how it works. Okay, now I get it. And at that point, you understand how to reproduce the actual issue. Well, so, but that is not all of it. There is a lot more. You can go multi-cloud. You can embrace chaos engineering. You should do health checks. I already talked about caching, immutable infrastructure. There's a lot of more things, and unfortunately, we're already out of time. So feel free to capture all of those terms and read up on those. There's a lot more stuff you can do. And if you have any specific questions, feel free to ask me or ask anyone else. But as I said earlier, from my perspective, the biggest part is you have to embrace the fact that there will be failures. There is no way to mitigate the situation. Embrace it and understand how to mitigate them before they hit the users really hard. And if you have questions, I'll be in the chat later on, and we have this like short session where we actually answer a few questions. And apart from that, I say thank you for listening in. Arigatou gozaimashita. And I hope you enjoyed this session. Thank you very much.